Time do I have?
Until they start here.
Until they go to sleep? Okay. Hopefully, hopefully I will not take that much time. I got 40 slides.
9 minutes is okay.
Oh, I should be done before 90 minutes, definitely way before 90 minutes. So yeah, anyways, I'll be talking about what we call virtual energy storage. So as Professor Mine mentioned, this kind of started with collaboration with Professor Mine when he was still at Illinois. We had a joint project, but the stuff that I'm going to talk about, my former students He Hao and Yashin Lin, they contributed a lot. There's a lot of experimentation that we did in an actual building, and that involved quite a bit of nasty software development. I mean, pretty heavy duty software development, not MATLAB or simple Python coding that I cannot do. So Tim Middlecoop was the responsible person for that. So yeah, okay, let me. So you must have talked about demand dispatch. Did you use virtual energy storage?
I think so, didn't I?
Okay.
Yeah.
So okay. Anyway, just to be on the same page, we'll talk about that. So this is kind of what you guys are learning in this course, right? So we want to go from those pictures to these pictures, and that's all good. But the problem is that now, because renewable energy is intermittent, so that causes a problem in keeping generation and demand in balance. And if you let the imbalance become too large, then bad things can happen, like blackout. So of course, this is a big problem now. So most people are talking about using batteries. And I think in this course, you guys are probably being told that we don't need batteries, right? Right? Well, I mean, we do need batteries, but maybe not as much as people think we do. And one of the ideas is to use loads, because we are now losing control. Earlier, we were controlling generation to meet demand, and demand was considered to be completely exogenous. Now we are losing control of the.
It doesn't matter. Just ignore that.
This is an exogenous disturbance that I was not planning.
No, you can high band for me. So click the fill
Okay,
high bandwidth.
High bandwidth control.
No disturbance. Come on, I need to know.
All right.
No.
Okay, cool. All right, thank you. All right, so the idea now is to kind of think about controlling demand, but of course you have to control demand in a way that users don't feel much of a difference. So kind of recap some of the stories that you have heard in this course is how do you control demand, and more importantly, how do you control demand so that they basically replace batteries effectively, right? So this is how a battery would be used to provide grid support. So y-axis is power consumption of the battery, x-axis is time. So when the power consumption of the battery is positive, that means battery is drawing power from the grid or from the solar panel, whatever. Negative power consumption means the battery is delivering power back to the grid, right? So this is charging, positive is charging, negative is discharging. Now if you look at a load, let's say an air conditioning system of a building like this building, or your home air conditioning system, refrigerator, all of our loads, that's how the power consumption is going to look like. Always positive, maybe zero at some times, right? But never negative. So it's not going to look like this. So the idea is to use some sort of intelligent control system, some software, to mess with it and intentionally make the power consumption now look like this red line. Right? Although the load doesn't really need it. We're going to do it so that the difference between this altered consumption minus what the baseline means what the load would naturally do otherwise, that difference looks like this. And that's like a charge discharging of a battery. So in effect, from the point of view of the grid, the building is, or this load is going to act like a battery, because the grid is planning for the baseline. It's not looking at a single building, but it's looking at like a whole collection of loads in its area, and it has prior knowledge, it has prediction of this baseline, and it's going to schedule all these generators, everything else to meet this curve, and then suddenly that, let's say at some point here, let's say solar production goes up, then the grid operator will have to send a signal to batteries saying that, hey, you guys charge more, consume more power. But instead of batteries, if you can make these buildings suddenly increase their power consumption, you're going to get that. You're going to absorb this extra energy from solar. So if I'm a grid operator, I don't really care who is consuming extra power. Is it the battery or is it a building or some other load? And therefore, if you can do that in a controlled fashion without causing any trouble, that's basically like a virtual battery. So that's how we call virtual battery. All right? VES, virtual energy storage. So you'll use this phrase VES all the time in this presentation. Two questions. One is, what kind of VES can a load provide without violating its quality of service? That's really important, right? Because if you say, well, we don't have renewable, we don't have batteries, so if we want to be reliant only on solar power, but there is no sun at night, well, everybody just turn off your lights and turn off your TV and go to bed, right? That is one solution, but of course nobody's going to be willing to use that solution. So maintaining the load's quality of service is important. Another one is what kind of energy storage. It's actually nothing to do with virtual. It's just what kind of energy storage is needed by the grid, right? So there are two things: what the grid needs and what these loads can provide. And you have to kind of think about, is there enough commonality? If the loads can only do 1 watt, grid needs a megawatt, gigawatt, well, there's no point. So one example, this is kind of the most intuitive example, is that take the air conditioning system of large buildings, or even in your home air conditioning system. But large buildings are even easier to think about. So if you look at the airflow coming into this room through that, I guess that's the diffuser, Naren, or is it the return air grill?
I guess
That's the diffuser. Okay, so that's where the air supply is coming into this room. Now, if I take that airflow, if I increase it by 10% for 10 minutes, and then decrease it again by 10% for the next 10 minutes, you and I would not feel any difference, right? So, but power consumption is going to go up every 10 minutes now, if I keep doing that, right? So that's like a battery charging and discharging every 10 minutes, if you take out the baseline. And the effect on temperature is nothing, because the building is going to act like a low-pass filter to this high-frequency input signal. And that happens because the structure has large thermal inertia, right? That's why we don't feel any difference. But if you increase, decrease, now very slowly, increase the airflow, keep it increase for like 2 hours, and then decrease, keep it low for the next 2 hours, now there will be a noticeable change in temperature. So now in this case, we cannot really use that. This would have been useful. This is like a battery charging and discharging much more slowly, but we actually cannot do that because it's going to lead to a violation of quality of service. So you can say, just by kind of thinking of just this thought experiments, you can say you can make building into a virtual battery that can charge and discharge at a fast pace, right, quickly, but it's not good for slow charging and discharging. So that's like a large energy. It's a low energy capacity, not high energy capacity. So then what does a grid need? Well, I mean, this is kind of a data from BPA. I'm sure you have seen data from BPA before in this course, right? So this is the net load, actual demand, baseline demand minus the wind generation. It's in gigawatts. And have you gone through this, Sean, this spectral decomposition thing?
No, the spectral decomposition I haven't.
No, okay, all right. So wanted to think about this. Okay, right now, why is this like a research problem? Why is everybody thinking about it? Is that you cannot use generators now to track this net load, right? This is what grid has to provide. Actual baseline demand minus whatever is produced by solar and wind. So remaining is this guy, and this is what everything else has to provide. And right now, generators cannot provide this because you see these very high frequency changes, like August 29th and 30, within a couple of hours, or this one, within a couple of hours, it went from 2 gigawatts to 6 gigawatts, 4 gigawatts. That's like 3 large nuclear power plants. Turn them on in 2 hours. Cannot do that, right? So that's a problem, but they can track like slowly varying signals. So you can take out that, you can low pass filter it, and you can say, well, that is slow enough that you can use conventional generators to track that. The remaining, you can see sometimes up, sometimes down, that's the zero mean signal, and that is something that you need a battery for. Now, if you had a giant battery, these differences are still in gigawatts because this is in gigawatts. So if you had a giant battery, gigawatts capacity, and then all your problems solved. But gigawatt batteries are going to cost you giga dollars. So So we don't have that. So that's where all this other stuff comes in. So if you take that signal out, this is a zero mean. It's basically charging and discharging, and you can decompose into many components. And depending on the time scale, you can use perhaps different loads. So this is the very highest frequency component of that, and this kind of changes every few minutes or every few hours. And based on our previous example of commercial buildings, maybe you can use thousands and millions of commercial buildings to track this signal, which is still in kind of megawatts, hundreds of megawatts, but it's fast enough that will not lead to temperature violation, right? Okay, so that's kind of the background. In the beginning, okay, so this is 2012, and 2012 is when I think our project, Sean, started a little bit earlier, but at that time the project was on energy efficiency on buildings. And Sean was Professor Mine was still in Illinois, and we kind of grabbed him into this project. And from the beginning, he was a bit skeptical about this whole energy efficiency thing. It's like, buildings can probably do much better job in helping the grid. And I was like, this guy's a mathematician. What does he know about buildings? But everything he actually suspected about buildings turned out to be true. We actually proved that that actually these things can be done, right? So, and then I had this very smart and aggressive graduate student, He Hao. And he had just was finishing up his PhD. He had like 6 more months to go. And his PhD was on control of large vehicular platoons. So it's like a large interconnected network control problem. And he had a number of very nice papers. But he had foresight. He realized that he's not going to get a good job by working on platoons. So at that time, 2011-ish, that's when these smart grid problems really became popular in the research community and also in industry. They were already thinking about all these renewable problems. That was 7 years ago, right? So one day he comes to me and says, Prabir, I want to work on smart grid. I'm like, God bless you, because I want to work on smart grid too. So let's work on smart grid. Well, our collaborator, Sean Mine, has been talking about smart grid and renewable integration and buildings. Let's see what we can do. So we actually wrote this paper. It was a bunch of simulations, but basically we put a little bit more analysis behind this picture I showed you. If you're very fast, no problem. If you're very slow, there'll be a problem. So the sweet spot of up and down, like a speed up charging, discharging, that buildings can do.
Can I make this one comment?
Sure.
So I got to present that at Elton in 2012. And somebody, actually it's Ross Baldick, you get a patent now. So we patented.
Yeah, our plan was to dominate the world with that, but that has not happened yet. Maybe soon. Yeah, patent actually got the patent, right. Oh yeah, and then so basically what I'm going to talk about is the technology behind how we made it work, all right? So before that, I have to talk a little bit about commercial buildings, HVAC systems. So commercial buildings, it's like all out of sight, out of mind, but these things are actually quite complicated. First of all, why focus on commercial buildings, right? Why not something else? Well, first of all, buildings is the thing to do if you want to do this, if you want to play these games, because all buildings combined in the US consume about 75% of all the electricity produced in the country, right? Buildings by far bigger consumer than anything else. So even if you tweak like 10% of that, that's 7.5% of the entire electricity production. And within that, HVAC is 40% of the total energy. It's not electricity, okay? Energy is both electricity and heating and other things. But still, HVAC consumes a big part. The other 40% is light right now, and the remaining 20% like cooking, this and that, right? But the share of light is going down. You know why? LEDs. So pretty soon, heating and cooling is going to be the major consumer of energy in buildings. Lights are going to be a very tiny fraction. And then there's a large thermal inertia in bigger buildings, so you can play these games easily. Vary airflow up and down, not going to be much of a difference. In your home, if you start varying airflow, it's going to be a little bit more limited in how much you can do. All right. So there are many, the other thing about commercial building HVAC systems is that there are like so many different types of systems. It's mind-blowing. So very commonly you'd see these. Oh, actually you would not see them. If you fly over Walmart, you'll see like dozens and dozens of those things, see, because they're hidden from your sight, right? So they're called packaged rooftop units, and they've cool down the air using a refrigeration loop and then blow the air. It's very similar to your home air conditioning system, right? And then, of course, you can play games like that, what we're talking about with these two, but they're a little bit tricky because they're motors that turn on or off. It's not easy to kind of slowly increase and slowly decrease. So instead of that, we look at these larger systems. So this is a messy picture, and this is the kind of system that is used in this building, for example. All right, most of the big buildings, large commercial buildings, including most of the large buildings in the campus, they use what is called a chilled water system. So instead of using a refrigeration loop to cool down the air, there is a chiller or chiller plant somewhere that uses refrigeration to produce cold water. It's called chilled water because it's really cold. So you don't call it cold water, you call it chilled water, right? And this chilled water is now supplied to all the buildings. So in this campus, we have 9 such plants. And these 9 plants supply this chilled water to all the hundreds of buildings in the campus. And the water comes into the building into something called an air handling unit. So I don't know how many air handling units are there in this building, probably 5 or 6 or maybe 2, 3, depends on the size. So the air handling unit is basically a giant air conditioner. But what happens is that the air from the building is, there's a fan that pulls the air out and it's ejected out to the outside, but not all. Some of it is mixed with fresh air from the outside. It goes to a filter. There's a fan that pushes the air into the building. But before you push the air into the building, because this air right now, it's outside may be hot, especially in Gainesville. Outside is hot. The return is kind of okay, kind of warm, but also humid. So then you have to cool and dehumidify the air, and that's the main consumer of energy. And that happens in something called a cooling coil. And the cooling coil, there are like control loops there that look at the temperature of this air and try to maintain that temperature 55 degrees Fahrenheit, so that air is cold enough and it's dry, all of that. And it's controlled by you controlling the flow rate of the chill water. So all that happens, then you get cold and dry air that goes into various zones. A zone, you can think of it as a room, like this is a zone maybe. Or maybe 2 of these rooms are a zone. And then there's a final level of control at the zone, because you blow that air, and there is a feedback control loop that looks at the temperature of the room, and if the temperature is too high, blow more air, because this air comes in cold. All right, and temperature of the room is low, then blow less air, and less and less and less, but it cannot be 0. Because if you do not send any air at all, then everything will get stuffy, you guys will get sleepy, or sleepier, I would say, all right? So, there's a limit how low you can make it, and then it becomes too low. At that point, you have to reheat the air. So there's a cooling, and then reheating, and then there are all these feedback control loops all over the place. It's a very complicated system. We don't think about it because it's out of sight, out of mind, but it is kind of complicated. And then if you go back to what is happening in the chiller and a cooling tower, it's even more complicated, but let's not worry about that. So for this varying air up and down to get virtual energy storage, I mean, where can you do that? Well, you can do it anywhere there is electricity being consumed in the HVAC system. And ultimately, all these consumers are finally just motors. Ultimately, that's all there is to it, a bunch of motors. And the chiller, compressors, the huge motors that compress, run the compressor loop. Fans, they're all motors. So right now, we're not going to focus on the chiller. We're going to look at the air handling unit fan, just the fan. The chillers are kind of complicated machinery, and in the beginning we were kind of afraid to deal with the chillers because that's they're complicated machinery and very expensive. We said, okay, let's not worry about the chiller. Let's just look at a fan. Especially in these modern buildings, they have what are called VAV systems. VAV stands for variable air volume, right? Meaning that you can vary the speed of the fan to change the rate of air going into the building. And that's done through a feedback closed loop system. And you can do that because there are these motors that come with something called variable frequency drive. It's not important what that is. What is important is that you can change these commands remotely through the internet nowadays to change the speed of the motor and therefore change the speed of change the power consumption as well as the airflow. Right? This is true for buildings that have building automation system. So all of the large buildings in campus have building automation system. Even these large, kind of nasty-looking buildings. All right. The old, nasty-looking buildings. The new, funky buildings, of course, they'll have very fancy building automation system. Oh, and this is a pretty large fraction of buildings. 30% of all commercial building floor space is served by such systems. And they already have this big fraction of that already has a building automation system. So you can, once you figure out how to do it in one building, you can deploy it in many buildings, right? This is why we focus on this. All right, so the thing is though, I mean, whatever kind of control we do, we have to work with the existing climate control system. And this climate control system, like I said, there are many layers of control. There's control happening at the chillers, control happening at these fans and the cooling chilled water supply system, and then there's control happening at the what are called, these are called VAV boxes. So right upstream of the, if you like make yourself tiny and then kind of go upstream through the duct, at one point you'll get to a box, and then there's a controller that is looking at the temperature of the room, changing the dampers to change the airflow, deciding to turn the reheat on and things like that. And then it's happening at every single zone. And then this fan speed controller, there's a control loop at the air handler, kind of up in the building, is trying to change the fan speed so that all these zones, all these rooms get sufficient air. So it's again a very complicated interconnected system. So we said, okay, let's start with something really simple. Let's get a building. Let's think of a building. There's only one zone, like a building with like one room. Well, where do you find such a building? Do they even exist? Luckily, there is actually one building in campus where you have a system like that, Pew Hall, University of Florida. So this building has 3 air handling units, and if you walk into this building, which is I don't know where it'd be, somewhere over there, I think. That way. Oh yeah, it's over there. All right. So there's a big auditorium in that building, and this whole auditorium is serviced by just one big air handling unit. So we can think of that auditorium as one zone serviced by one air handling unit. So we don't have to worry about all these interconnections. So this is what we're going to focus on. All right, so we're going to use the fan, and there's a time scale that I'm going to get into. I know I said earlier that you cannot vary the airflow too slowly. The question is, how fast do you have to do it? Turns out we have to do it in this time scale or this frequency. And why is that? We'll do some experiments to figure this out. So this is where that high frequency phrase comes from. High frequency doesn't mean 2.4 gigahertz, okay? It means 1/10 minutes in this context. All right, so this is the plan. The balancing authority, I mean, this is kind of thinking ahead how this type of technology will be deployed in practice. We didn't do all that in the building, in the experiments. So the balancing authority is going to send some sort of a reference power deviation signal. It's called delta P BA, and that'll be in gigawatts, right? It's like these signals that I showed earlier. Of course, every building can only provide a few kilowatts. So first, you have to band pass filter it and create a reference for the building. So what is this reference for? Is the reference for the power deviation of the building from its own baseline, right? So somehow there we have to design a controller. We call it ancillary service controller. You can call it VES controller, virtual energy storage controller. It has to change something in this building to affect that change in the power consumption, and that has to be that change in power consumption has to track this reference, right? So this reference, we assume it will be created locally, maybe on site, to bring this megawatt signal down to kilowatt, but also, and more importantly, to kind of get the right time scale. So it's not asking you to vary power for the next 2 hours and then decrease for the next 4 hours, because we know that cannot be done. All right, before we can go, design this controller, to think about, okay, what is the actuator signal? What are we going to change among all the things that can be changed in a building to affect that power consumption? And how do you measure this power deviation? Because we are trying to change the power. So this is power minus baseline power. What is baseline power? Baseline power is what the building would have done had the grid not been messing with it, right? So you can't measure that. That's a counterfactual. This is what the building would have done. So we have to figure out in real time what the building would have done had I not been there to do all this. So how do you do that? Okay, must work with existing building equipment, must work with existing building climate control system, right? So cannot, because if you insist that this can only work with completely new design, then this technology will not be adopted widely and will not have much impact. And of course, it cannot change indoor climate to any perceptible degree, cannot have any unintended change in electricity consumption in the chiller. We just want to focus on the fan, make sure that whatever we do in the fan, it doesn't kind of somehow, without our knowing, affect what is happening downstream and changing everything else. So now we will look at what this climate control system looks like before we can figure out where is the knob, like where can we kind of mess with it to do what we want to do. So I'm simplifying what is happening in the climate control system into the simple feedback loop. So all these subscripts B mean baseline. That's what normally happens, right? So building is affected by disturbance, when a heat produced by us, solar radiation coming from outside, and it produces a temperature, and that is picked up by a thermostat temperature sensor somewhere, and gets compared to the reference temperature. That's the set point you enter in the thermostat. This room does. Oh, there is a. I don't know what that is. This is for something else, but I guess because this is actually not where the thermostat is, but in one of these rooms there will be a thermostat in which you can enter the desired value of temperature. That's the reference temperature. Is it a thermostat? I don't know. It's too well protected. Maybe it is. All right. So this error goes into a climate controller, and this controller is a computer board that's somewhere in this building. We don't see it often. And it decides how much air to kind of supply into the building. Right? And that's a set point for the airflow. So M represents here mass of airflow, right? Or flow rate of mass flow rate of air as reference. And there is a fan motor, but there is also another controller that changes the voltage and the frequency, all of those things that we don't have to worry about, to change the speed of the fan so that the actual airflow rate matches with the reference airflow rate. So there are sensors to measure airflow rate as well, right? And of course, when you change the airflow rate, because of that, it changes the fan power consumption. That's the baseline fan power. So that's a simplified version already, and we are going to simplify it further. Assume that T reference is a constant, which usually is the case, so we can get rid of this. You can kind of linearize or do a coordinate transformation, so there is no extra input coming here. And this whole thing is a closed loop transfer function. You can write it as like one transfer function. Okay. Reference for the mass flow goes in, actual mass flow comes out, and correspondingly some sort of power consumption of the fan. Right? Okay, so now our actuation. If I want to vary the airflow rate, because this is a reference command from the controller that goes into the lower level control loop of the fan, so it goes through a wire, right? This signal goes through a wire from one controller board to another controller board. So we're going to go in there, cut that wire. All right. I'm going to cut that wire and inject another signal there. So if the controller says I want 4,000 CFM, cubic feet per minute of air, we're going to go in there and add another 200 at one point. Another point of time, we're going to subtract out 200. So instead of 4,000, I'll get sometimes 4,200, sometimes 3,800. Right? That's how I'm going to change the reference for the airflow. Now the fan controller doesn't know that I'm messing with it. It is going to just see this reference signal is changing, and it's going to do its own control to make sure that this airflow rate tracks this input. Right? And of course, this new airflow is going to hit the building. That's going to lead to some temperature variation from the baseline. So, and then this temperature, the new temperature, is being read by the climate controller, and it's going to go on. So only thing we're going to do is we're going to go in there, cut that wire, and add this signal. Now we are actually not going to go with a with a wire cutter and actually cut the wire. We'll do all this remotely through the internet. So this building automation systems, there's a separate communication protocol for doing that, for sending these commands, and you can send commands with higher or lower priority. So the software that Tim Middlecoop wrote, it allows you to kind of change this priority of this signal. We kind of take whatever the building automation system is doing, we add numbers, change the priority, send it to the fan controller, and it does that. Right? So equivalent to kind of going in there, cutting the wire. So now that we have got our actuation is going to be this reference for the airflow. We're going to change that, or a change in the reference for airflow. That is going to lead to a change in the power consumption. We still have to measure it, right, somehow. And it's going to lead to a change in temperature. So our goal is to make sure that this change in power consumption tracks whatever the grid is asking for, and this change in temperature is like really small. Those are two things we have to do, right? So there has to be a controller that has to change this to make sure delta P tracks the reference and delta T is small, imperceptible. So that the climate control system doesn't have any idea what's going on, because it doesn't see any change in temperature. It only reacts to change in temperature, right? And this immediately tells you that this V is actuation command U, which is U means this change in the reference for the airflow. Because it looks like a disturbance to the climate controller, you have to make sure that the time scale or the frequency of this has to be limited in a range, limited to a range in which the gain of this transfer function, okay, airflow to temperature is very small. So if you look at the transfer function, airflow rate to temperature, and it's got a low gain in some frequency. So if you now change that command U, temperature variation is going to be negligible, so the climate controller is not going to do anything at all. Otherwise, this appears as a disturbance, just like this other disturbance of the climate controller. If the effect of this disturbance is measurable, the climate controller is going to pick that up and is going to reject that, because that's what feedback loops are designed to do. Then what we are trying to do is going to fight with the climate controller, and it's just not going to work, right? So the airflow rate command to the power in that frequency range must have high enough gain, and airflow rate to temperature in the same frequency range must have low gain. So this is what Yash and Lin did. This is experimental data on that system. It's called a sine sweep experiment. I don't know if some of you might know what this is. So you send a sinusoidal signal into the system, record the output, figure out the gain and the phase. You do it frequency by frequency. You can experimentally determine the Bode plot of the system. So we actually experimentally obtain the Bode plot of the system. What is the system? It's the transfer function from airflow rate to power deviation. And it's a nice second order type behavior, and it's got high gain in this frequency range, and then the gain goes down. I say high gain, although the value is negative 50 decibels, is because nominal CFM is like 4,000 CFM, and the power is about 2.5 kilowatts. So that's why the number looks small, but if you change the airflow by 10%, it's going to still have a pretty large impact on the power consumption. So because the gain is kind of flat and high in this frequency range, this is the range in which we are going to, and this is sufficiently high frequency, all right? This is 1 minute to 10 minutes, or 1 over 10 minutes to 1 over 1 minute. It's sufficiently high, this frequency range, compared to the bandwidth of the climate control system. So this is the range in which we are going to vary our airflow, and we will vary the power consumption. So that's why we're limiting. In the beginning I said this whole experiment, or this whole control system, will be limited to providing VES at this time scale, 1 minute to 10 minutes. Why? Came out of this experiment. For this building, this is the best range. You can of course go lower, but the lower you go, then you start fighting the climate control system, because then you'll have an effect on the temperature. So yeah, well, we don't have experimental data for how this thing affects the temperature, but because the temperature measurements are really slow. But we did a lot of modeling work to convince ourselves that in this range of frequency, where the power consumption reacts quite fast to airflow rate, temperature doesn't react at all. So it's like, okay, this is the range. We don't want to go slower, because then it's going to start affecting temperature. It's going to be picked up by the climate control system. The two things are going to start fighting. So we're going to pick this range of frequency. Okay. So that problem is solved. Okay. So we don't have to, we know, at least we believe, that we are not going to now affect the climate control system. These two control systems kind of work in different frequency ranges, so they don't see each other. The last problem is to measure this delta P. To measure the power, we can actually measure power consumption in real time, but that's not enough. What we need is power consumption minus the would have been power consumption, right? So how do you do that? Well, this is a nice trick that we realize, well, the would have been power consumption would have been because of the climate controller. And the climate controller is operating at a much slower time scale. So if you just take this total power consumption signal and if you low pass filter it, keep only the high frequency component, that component is coming because of what we are doing. The low frequency component of this signal is what is happening because of the climate controller. So if we just low pass filter the signal, the low pass part is what is happening because of the baseline, and the high frequency part is what is happening because of our VES controller. So in real time, we just do a high pass filter to figure out the delta P, what is happening because of our messing with the system. All of that work because of this time scale separation. That's the key. And you might have noticed all of this doesn't require any fancy non-linear stochastic PDE, none of that, right? It's all kind of undergraduate style classical control system design and analysis. That's all you need to make that work. And yeah, it worked. So this is the closed loop. So the controller is a lag controller, right? It's just very simple. And implemented this using Tim Madlikov software, and this is how the reference tracking performance looks like. This blue line is the reference, and this came from PJM. You guys have all heard of PJM, I assume, multiple times, right? Yeah, this came from PJM. This is a signal they provide. If you are a battery or a flywheel operator or anybody who wants to provide ancillary service, or a generator that wants to provide ancillary service in PJM territory, you have to do a test and show that you can track this signal with a score of at least 0.75. We showed that, yeah, we can get that score. Right? There's some tracking error. Most of it is actually measurement noise because this measurement is not very good. So had this building been in PJM territory, you could use this building to make some money. Right? We actually estimated we could make about $1,300 a year if the PJM prices remain at 2013 numbers. But of course, what's going to happen is that if all of the buildings start doing that, then the price is going to collapse, and then you make nothing, right? So that's the problem with all this price-based coordination. The standard assumption every paper starts with, we assume consumers are price takers, right? But beyond a certain scale, we are not a price taker. Anyway, so this is the temperature during the test for the whole 24 hours, and there's some normal variation, but you cannot really see that in this 40 minutes when the test was done, there's no change in the internal climate. Yeah, this is published here. Okay, so this is basically I don't think it's really worthwhile going in there. This is software that Tim Madlikov wrote, without which